Hello, this is Gregory Maxwell, and this is a short video explanation prepared for my STA 2023 class discussing conditional probability and using it in conjunction or in collaboration with probability trees or tree diagrams to work out probabilities of certain situations. Now, let me just quickly get into this. Conditional probability is a probability of an event obtained with additional information that some other event has occurred. In other words, if we're trying to find the probability of B, given that A has occurred, we're saying what's the probability of getting B if we know that A has occurred, or if we assume that A has occurred. The notation of conditional probability is P of B with a vertical bar, like half of an absolute value, a vertical bar A, and it's read the probability of B given A, the probability of B given A. So the probability of B given A denotes the conditional probability of event B occurring given that event A has occurred. And that phrase, given that, is very important. That phrase, whether stated outright or implied in the context, is the indication that we're dealing with a conditional probability. And I'm going to show you here how to approach the conditional probability in the correct way. So again, the conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that B will occur under those circumstances. Formally speaking, what it's saying is we want to find the probability of B given A. What we do is first identify the probability of A, and we're going to put on top of that the probability of both combined. So if I may, we have, I'm going to kind of draw a little Venn diagram to illustrate what I'm talking about here. So I have a little box that represents all the possible situations. And then we have two events. I'm going to represent those events by circles in the Venn diagram. We have event B and event A. Now, we want to find out, and I don't have my writing utensil with me in this one, so I'm going to just have to type the symbols here. So we have event A, let me put that one first, and then we have event B in the larger circle. Okay, now it doesn't matter which circle is larger. All we want to know is what would we represent by the probabilities. So what we're going to do is event A is covered by the situations in, let me put a few labels here. It's covered by the situations occurring in section 1 and in section 2, which I'm gonna indicate right here. So event A are the situations in both these sections, event 1 and 2. That means the circle A. And the event B is in 2 and 3, but where they overlap is only if section 2. So what we would do is to find the probability of B given that A has occurred is, what we say is, let's ignore everything except what's in A, and then how much of that is also in B. Ignoring everything that's in except for what's in A, how much of that region falls also in A. So that's what this symbol is saying here. So if I may shade it, we're only looking, let me grab this, we're only looking at what is in region, in circle A. So I'm marking that with these highlighted regions here, which is region 1 and 2. And then we're going to say from that, which out of that region is already shaded is also in region B. So we're only looking at parts of A and for the consideration, and only those parts of A that are also in B is considered. That's how we do it. What's the probability of falling into the intersection divided by what's the probability of falling into A? What's the probability of B? Given that we're looking only at the parts of looking only at A situation, we ignore everything else. So how do we approach that? We're going to look at it in three ways actually. The first way is by just looking at a table. This is called a two-way table because it gives information in two formats. And we're going to also look at it by just using the formula and using a common sense approach with the formula. And then thirdly, we're going to draw a tree diagram and reason from there. Let's take a look at the example here that I have. I got this off a random exercise off the internet, and it was actually already done. So what I'm going to do is read it and explain as I go along and uncover the answers as we go along. So the table to the right lists employees' years of service at a company broken down by gender. So this is the number of years of service: 0 to 4 years, 5 to 9 years, 10 to 14 years, and over 14 years. This should be over 14 years. So it should be not 14 plus, but more than 14 years. So let's understand that. Then we have also males, females. Now the total number of employees they surveyed is 100 employees. 12 of the males have served for 0 to 4 years, 6 for 5 to 9 years, 17 for 10 to 14 years, and 21 for more than 14 years. When you add up all of those numbers, we get 56. That means we have 56 male employees that are in this survey. All right, 12 plus 6 is 18. 18 plus 21 is 38, and 38 plus 17. Oh, sorry. 18 plus 21 is 39, and 39 plus 17 is 56. Then we look at females. 8 females are 0 to 4 years, 9 females are 5 to 9 years, 13 females are 10 to 14 years, and 14 females are more than 14 years. When you add those up, we have 8 plus 9 is 17, plus 13 is 30, plus 14 is 44. So we have 44 females in all, and that we add those up, we have 100 people. We have 20 people in all, less than 0 to 4 years, 15 people serving 5 to 9 years, 30 people serving 10 to 14 years, and 35 people serving more than 14 years. You add all of those up, you get 100. So we know the total number of people is 100. So the first question is, what is the probability of randomly selecting a female employee? This is not a conditional probability because they do not give us any restriction. They do not give us any restriction on the choices we're choosing from. All they say is, what's the probability of getting a female? So we look at all the females, which is 14, and divide that by how many people in all. So when we do that, we get 44 over 100. 44 female employees out of 100 in all. That's not conditional probability. That's just straightforward probability. What I want over what's possible. Now, how do we know we're dealing with conditional probability? If the words given that are either stated or implied, then whatever comes after that is what we're restricting ourselves to. That's the conditional probability. So what comes after the word given that is the only part we're considering. So since we say given that the employee is male, then we're only looking at the male employees. We don't look at anyone else. So we're only looking at the 56 employees that are male. We're ignoring all the other situations and only looking at that row with males, 56 employees. And then they say, what is the probability that they have less than 4 years of experience? So what we're going to do is look at the 56 employees that are male, and then from that row only, we're ignoring everything else, but only from the row of 56 males, we look at those that fit the less than 4 years of experience. That means 0 to 4 years, that's 12. That means our probability is not 12 over 100, it is actually 12 over 56 because we're only considering the 56 males. We only focus on the male row. So we have 12 males in the 0 to 4 and 56 in the given that. Given that the employee is male, we only have 56 to choose from, so we do 12 of those 56 males out of the 56 males in all. If we go to the next part, we do see the same thing. They say given that again. So once they say given that, we only focus on that region. So the given that in this case is given that the employee has between 10 and 14 years of experience inclusive. That means we're only looking at this column, which has 30 in all. What is the probability that the employee is female? So out of only this column, we ignore everything else but this column, which has 30 in all. What is the probability that someone is female? We look at the 30 and look how many are female. So we only look at the column of 10 to 14, and we have 30. That's the denominator, and then the numerator is a 13 that's taken out of that 30. And so we have 13 out of 30. Fourth question. Given that the employee has more than 14 years experience. So again, once they say given that, we're only looking at that region. So more than 14 years is this column here, which is 35 people. What is the probability that the employee is male? Out of those in that column only, ignore every other column, we have 35 in all. How many are male? 14. So the answer is then going to be 14 over 35. Oh, sorry. More than 14, 21 over 35. I misread. I read the females instead of the males. So there are 21 males out of the 35 in all that come under that given that condition. 60%. Now let's try another type. So now given that the following information, probability that you're in D is 0.7, probability in E is 0.2, and probability in both is 0.15. Find the probability of being in D given that you're in set E. So what we're going to do is our denominator is the given that. So this is a probability of being of D given that we're in E. So what we do is we find how many things are in E. And that is 0.2. So we're going to divide by 0.2. And then out of that, how many of those things in point E are also in D? That's 0.15. So the answer for this is 0.15 divided by 0.2, which basically works out to, if you divide it on your calculator, is 15 over 20, or 3 out of 4, 3/4, or 0.75. So as you see, what I did was I only divided by the given that, the probability of P given that E, we only look at what's in E, and then that's the denominator. And then what's in the numerator would be what is shared between the two. Now, if we do it the other way, what's the probability of E given D? Now the denominator is not E, the denominator is D. So my denominator is 0.7. And then we are going to put on top how much of that 0.7 comes from E, 0.2. So then my answer is going to be 2 divided by 7. And you can work the decimal version of that on your own. Now, let's do another example here. This next example, it says, Andrea is a very good student. The probability that she studies and passes her mathematics test is 17 over 20. If the probability that Andrea studies is 15 out of 16, find the probability that Andrea passes her mathematics test given that she has studied. By the way, again, these questions are just taken from a quick search on Google of conditional probability worksheet. And if you do that search, you'll find these same questions and many more that you can practice and also see some answers to some of them. So in this situation, we want to find the probability. That Andrea passes her math test given that she studies. So let's type that up. So it's just giving it a moment to load here. is the probability that she passes the test given that, that's that vertical bar, she studied. Now, how do we set this up? We need to have a denominator. The denominator would be what comes after the given that. So what's the probability that she studied? If the probability that Andrea studies is 15 over 16, then that's what I'm dividing by. So I'm going to be dividing, and what I'm going to do is use the division symbol. Let's find it over here. The division, we're going to be dividing by the fraction 15 over 16. So let's divide by 15 over 16. Now, what are we dividing by 15 over 16? We're dividing the probability that she passes, she studies and passes. So the probability that she studies and passes, that means they intersect, is 17 over 20. So that's my fraction there. I'm going to divide 17 over 20, which is the probability of that she both studies and passes, and divide that by 15 over 16. Now, you can do that on your calculator, or you can just use a little arithmetic here. When you're dividing two fractions, you multiply by the reciprocal of the second fraction. So I'm going to indicate that here. And let's just see if we can write the answer down here. So that's equal to, and let's see what we got here. We're multiplying. We notice that 16 and 20 have a common multiple of 4, a common factor of 4. So I'm going to divide by 4. 16 divided by 4 is 4, and so we do 4 multiplied by 17, and 4 multiplied by 17 is 68, and then the denominator, then you have 20 divided by 4 is 5. 5 times 15 is 75. So we're going to end up with 68 over 75. 68 over 75. And you can work out the corresponding decimal version for that number on your own. So the result of this is indicated right here. Let me put it so we can see it more easily. And there we go. The symbol is a little out of whack here, but you get the idea. The probability that she passes, given that she studied, is the probability of both studying and passing, and then divided by the probability of studying, because you divide by the part that comes after the given that. Now, for the last component of our lesson, I'm going to talk about a question I made up, which is indicated here. And we're going to use what we call a probability tree, a tree diagram, to indicate the probabilities. The probability of it raining on a given day is 30%. If it rains, the probability that Carl is late for work is 22%. If it does not rain, then the probability that Carl is late for work is 15%. Then the question is, draw a tree diagram to represent the information. Now, there are two basic things going on: the issue of rain and the issue of being late. So either it rains or it doesn't rain, or it's late, or Carl is late or not late. So we're going to start off with a probability tree here. The first part I'm going to do is I'm going to draw two branches. And the two branches represent the two first possibilities. If there are 3 possibilities, I would have drawn 3 branches from the same node, from the same end point right here. I call that a node. And so what that branch that I drew here, it's either represents it raining, so I'm going to draw a little R there for rain, or not rain. So those are the 2 possibilities. Either it rains or it's not rain. So to represent not rain, I'm going to put a little bar over the top. Let me see if I can find that here. If not, I'll just switch it to another symbol for ease, since I don't want to spend the time searching for symbols here. There we go. So either it's R or it is R, the complement of R, not R. So let's see what we have here. Find the probabilities that, so the first question is, the probability that it is raining is 30%. So we're going to write that as a percent right here. I'm going to write it as a decimal, but it's the same thing as a percent. So it's 30% is the same as 0.3. Now, the first thing about probability trees I want to point out is if any items come from the same node, their total probability is 1. And we must draw it so that what goes along one branch can also go along another branch. They should be mutually exclusive. So either it rains or it does not rain. Those are the only two possibilities, and they do not overlap because they're complements. So if the probability of rain is 30% or 0.3, then the probability of not rain is the leftover 70% or 0.7. Since those two come from the same node, then they add up to be 1. Those two probabilities must add up to be 1. Now, the next situation is about being late for work. So we're going to draw another couple of nodes from the R, another couple of lines, or what I call branches from the R. One branch represents Carl being late, so I'm going to call that L. And the other branch represents Carl being not late. So we're going to look at Carl being either late or not late. So we go back again, find some symbol, and then we'll use that. So either he was late or he's not late under the condition of it raining. Again, we do the same thing again. Under the condition of it not raining, either he was late or not late. So we can work from that. Having a little difficulty here with my functions. So again, these two, late and not late, come from the same node here, and late and not late come from the same node here. So let's see. It says if it rains, then the probability of Carl being late is 22%. So we go that under the rain situation, the probability of being late is 22%, which I will write as 0.22. That's the decimal. That means the leftovers would go to it not raining under that same situation of him, in not being late under the same condition of it raining. So if it rains, then his probability of being late is 0.22. If it doesn't rain, then his probability of being late is 0.7. Sorry. Let me repeat that. If it rains, its probability of being late is 0.22, which means that if it rains, its probability of not being late is 0.78. Because these two things come from the same node, they should add up to be 1. Just like these two come from the same node, same point there, they add up to be 1. In the case of not being late, if it does not rain, then the probability of being late is only 0.15. So if it's under the case of not rain, him being late is 0.15. Which means under the condition of it not raining, him being late would be the leftovers, 0.85. So let's see how that looks here. And then again, those two probabilities should add up to be 1. Now, that's the tree diagram. Now I'm going to add some more modifications to the tree diagram to indicate one more thing. When we go in vertically down, we're looking at either this situation or this situation. But as we go along branches, we're saying this situation and this situation. So for example, if I go from here to here and then from here to here, I'm saying the probability of it raining and he is late as we go along from here to here and then here to here, from R to along R and then along L means probability that it rains and he is late. So I'm going to rewrite those now and say, okay, for this first case, this is the probability that it rains and Carl is late. We're going to see what that works out to be. So we have that example there. That's the first one. This one we'll put right here. Then let's do another one, but this time is for R and then L complement, which we'll then write as the probability that it rains. That's the L1, that's the R, and he is not late. We're going to see what that works out to be. We're going to do the same thing again, but this time, oh, I need to make a little correction to my notation here. Made a little error. All right, so now we have it. And next, we're going to look at the next one, which is the probability that it does not rain and he is late. So let's fill that one in. The probability that it does not rain and he's late. Let's see what that works out to be. And then finally, the last case is the probability that it does not rain and he is not late. We'll see that what that works out to be. So those are my situations here. Now, when we work this out, ultimately, these four situations come from the same node. The probability of rain and he's late starts at this node and stops here. Probability of rain and not being late starts at this node and continues and stops here. Probability of not rain and him being late starts at this node and stops right there. And the probability of it not raining and him not being late starts at the same node and stops here. So these four situations should add up to be 1. Now, whenever we see and, we multiply. So when we go along the branches, we're going to multiply the answers. So for this one here, we're going to multiply 0.3 by 0.22. And I'm going to give the exact answer here. I'm not going to round. I'm going to go all the way. 0.3 multiplied by 0.22 is going to give us 0.066. So 3 decimal places. And then we're going to do the same here. 0.3 multiplied by 0.78. Because when we do an and, we multiply the probabilities. It's probability of R multiply the probability of L given that R has occurred. So let me redo that part there. A little glitch. So 0.3 multiplied by 0.78. And that works out to be 0.234. And then we continue. Same idea. We're going to go down to probability of R, not R, and L. So in this case, we're talking about 0.7 multiplied by 0.15. And that works out to be 0.105. And then finally, we're going to be multiplying 0.7 multiplied by 0.85. And that's equal to 0.595. So if we are right when we add up all of these numbers, we should get 1. So please note that I'm going to just indicate that with a little line here. Well, let me just indicate it over on the right side here. So then I'm going to indicate here that when we add 0.066 plus 0.234 plus 0.105 plus 0.595. Let's see. You can check that on your calculator. 0.066 plus 0.234 is going to be 0.3. And 0.105 plus 0.595 is going to be 0.7. And that happens to work out to be 1. So we already have that. I'm going to just change the color there just to show that as a side note. So I'm going to say note. So that confirms what I said before. Now, that's the end of the tree diagram. It seems like it took a long time to do part A, which it did, but it actually made it easier for us to do the rest, because now they say find the probability that Carl is late to work on a given day. Now, if Carl is going to be late to work on a given day, he's going to be late to work in 2 possible ways. He's either late to work when it rains, or he's late to work when it doesn't rain. So the probability of Carl being late is either when it rains or when it doesn't rain. So I'm going to write that down. So let's see what we got here. See what we have. So probability of late is equal to probability of that plus probability of R and L. In other words, let me write it the other way around. In other words, there are 2 cases that he could be late, and those cases is either that he's late when it rains, or, and if it's an or, you add the probabilities, he's late and it doesn't rain, which makes our life very easy now, because all we have to do is add the 2 probabilities. I'm going to make a little adjustment here. And so my answer becomes simply adding 0.066 to 0.105. Those are the 2 cases where Carl was late. So it's 0.066 plus 0.105. And those work out to be 0.171. Let me see if I have any space for that one. I might not, but let's see. Let's hope. And that is how we do that. Making it a little smaller for the sake of being able to be seen. That's it. The probability of being late for work is add up all the probabilities of each case. Either he's late when it rains, or he's late when it doesn't rain. Find the probability that it rains and Carl is not late to work. That one is actually easy because we already have that one. It rains and he's not late to work. So look for where it rains and he's not late to work. That is our example right here. So that answer is 0.234. No extra work necessary right there. Now, let's see what we have next. Find the probability that it rains given that Carl is not late to work. So now we have to find the probability under this condition that he is not late to work. So when is Carl not late to work? Well, Carl is not late to work in two cases. This case where it rains and this case where it doesn't. That's going to be the denominator of my expression. So I know I'm going to be dividing by the sum of 0.234 and 0.595. So that's going to be my denominator. That's the total probability of him not being late. So what's the probability of him not being late? It's the sum of those two pieces. Out of those two, because we're only considering now from the given, only from the given that, out of those two, what is the probability of it raining? So we look at which of these two with him not being late also has rain, and that's the top one, and that probability is 0.234. So now we will divide 0.234 by that total, and we'll see what we get. So that's what it works out to be. So let's see what our answer works out to be here. It's going to be 0.234 divided by the sum of 0.234 and 0.595, which that sum is 0.829. And if you divide that and simplify the fraction, our answer works out to be 234 over 829. We just move the decimal point. They have no common factor. You can simplify. I want to leave it as a fraction in this case because it's exact. But you can get the corresponding decimal, which is 0.282, which is actually the approximate value. Now, last situation. The last situation is what is the probability that Carl is not late to work given that it did not rain. That one actually we don't even have to do any work. We look only in the given that it did not rain. And how much of that is from him not being late to work? 0.85. That's it. So for this one here, I'm just gonna draw a little arrow over to the right hand side to show how I did that question there. So I'm going to draw a little arrow there. And what I'm going to say is I'm going to say, all right, we're going to divide. We're going to do a little work here. So let me write that up here. We're going to write the probability of Carl is not late to work given that it did not rain. So the probability that Carl is not late to work and then we have given that it did not rain. So again, what we did was we looked at only the part without rain, and so how much of that was he was not late. It's 0.85. To do it the longer way, we would say, okay, what's the probability of it not raining? That's 0.7. We know that because it told us that. And then out of that 0.7, how much of it is so how much of it did not have him not being late? It's 0.85. So let's see how we do this then. So the formula is we take a fraction, we find the probability of him of it not raining, that's 0.7, and then we find the probability of it both not raining and him not being late, which is 0.595. If you have to do that division on your calculator, you'll find that that answer works out to be 0.85. 0.595 divided by 0.7 is going to be 0.85. We did not really need to do the work. We did not need to do the work because what we're saying is, under the condition of it not raining, what's the probability of it not being late? 0.85. That brings us to the end of this example. Now, there's a lot here that you need to review. I would strongly recommend that you spend some time going through this material and making sure that you understand it. Review the video if you need to, pause it, try the exercises on your own, and then check to see if you are on the right track. That's all for now, and that brings us to the end of this short, well, relatively short lesson on conditional probability with examples.